To last time, I think, and a reminder that a lot of what we talked about, I think, last time was about measurements and how to properly take measurements. And remember, there's always some degree of uncertainty when you do take a measurement. And that degree of uncertainty is really dependent on the piece of equipment that you're using. So as we talked about, it is always important, no matter what sort of piece of equipment that you use, maybe outside of something that's a digital sort of display, that if it's something that has markings and you need to sort of take the reading, you want to make sure you understand what does each of these markings mean. And remember, there usually is always sort of like a larger sort of marking, and there's usually, again, always more of a smaller type marking. So, for example, I think we looked at a sort of ruler situation. And again, when we look at the larger markings on most pieces of equipment, they actually do have numbers next to those markings. So again, in this case, we can see that the larger marking, the difference that we see there is basically 1 centimeter. Then the also really important is to realize what the kind of smaller markings are. And we really want to count up how many smaller markings there are really between those kind of two big markings that are on there. Remember that when we count, we want to sort of count the little markings correctly. So we never really start on a big marking to a big marking. We always start just past the last large marking and go to the next large marking. So here, I didn't lose my ruler. We would start right there. And again, that would be sort of our first small marking. That would be our second, our third, our fourth, our fifth, our sixth, our seventh, our eighth, our ninth. And again, we would stop at the next sort of large marking, which would be basically 10 markings. So in this particular case, since there are 10 markings between really a sort of length there of 1 centimeter, each of the smaller markings are really found to be 0.1 of a centimeter. We could also get that by taking 1 divided by 10, right? There's the 10 markings that we have will tell us that. When we go to take a measurement, no matter what type of measurement, again, that it is, just kind of lay it up there. Once again here, because this is 1.1, that would be 1.2, 1.3, 1.4, 1.5, and again, all the way across. As we talked about, there should always be really measurements that no matter who takes a peek at it, really everybody should sort of agree that, this thing is at least, in this case, this long. And those are sometimes referred to as certain numbers. And whenever you take a measurement, you should always record all the certain numbers. So in this case, again, I would record 1.5, which would be my certain numbers. And we could clearly see here in the picture that it's not exactly 1.4. I know I should record 1.4, which would be a much better number than the 1.5. I'm pretty certain of that. Let's try that again. 1.4 looks good. 1.4 there is the least it is. It's not exactly 1.4, and it's obviously not exactly 1.5. So that is really where the estimation comes into play and really where the uncertainty comes into play. So again, what you typically want to do is sort of in your head, kind of break up that distance between those two small markings, maybe sort of equal distant, and sort of figure out about where you think that is maybe lying. Again, if you think it's like dead center, you could put it as a 5. And just so you know, it doesn't always have to be a 5. Clearly, if maybe my line, I'll extend my line in this case, maybe my line is a lot closer to the next marking, right? So you wouldn't want to record 5 for that last number because it's clearly past halfway. So, you could use any number really. Again, if it's a little closer to the next line, maybe you want to record 8 or something like that. And then obviously the units that go with it. Here, our 8 would be what is sometimes referred to as the first uncertain number. And the importance of when you take a measurement to always record all the certain numbers plus the first uncertain number, that is, again, essentially what significant figures are. So taking all that together is significant figures. And as we talked about there, that essentially means that this guy here would have 3 significant figures in this particular measurement. With the uncertain number or digit, or the estimated digit in this case being the 8. And in most cases, most people think of it as being like plus or minus 1 of that last number. So again, you're saying, I think it's 1.48, but maybe it's like 1.49, maybe it's like 1.47, but it's somewhere in that range. I'm fairly certain it's, in that ballpark. Um, Other important things that we talked about on this is even if you, again, I'll just draw a second line here. Even if you, again, are measuring something that is like dead on a marking, and you have the ability based on that sort of equipment to go to 2 decimal places, as we see here, you do need to continue and keep that. So again, this would be like 1.7. We would want to record 1.7, and we would need to add the 0 in there to be our uncertain digit in this case. And that means that this guy would have 3 significant figures in this case. These 2 being our certain numbers, this being our uncertain number, our estimated digit in this particular case. As we talked about, I think last time, if you just sort of loft off that 0 and just go, hey, 1.7 looks great, that now has how many significant figures? And the uncertain number would be 7. So again, in that case, you're basically saying, I think, well, it's 1.7, maybe it's 1.6, maybe it's 1.8, which clearly is a much bigger range of uncertainty and error, which you really shouldn't have using a piece of equipment like that. You should have this sort of range of error, which is like that, where that little circle is. And again, sometimes people think, oh, it doesn't really make a big difference, if you sort of add the 0 or not, but you do need to make sure that you maintain how far you can take that reading. And that may require in certain cases to put a 0, especially if you're kind of dead on a marking or something like that. Other common mistakes, again, as we talked about, I think last time as well, if you have something that is digital, typically speaking, all those numbers are important, so you shouldn't lose any of those digital sort of numbers as well. Now, if you're really maybe not sure how far you should take the reading, in most cases, and not 100% of the time, but probably 9 times out of 10, you typically could take your reading to one more place to the right of the smallest marking. So in this particular case, the smallest marking is the first decimal place. So we're able to go one more place to the right of that and take our reading to the second decimal place. If you're really not sure to remember that either, if you can figure out the smallest markings, what they represent, all you simply have to do is divide the smallest marking by 2, and you'll get a number like this. It'll always probably end up being a 5 in a lot of cases. The 5 is not important, but what this will also tell you is that is how far you should take the reading, to 2 decimal places like we did in this particular case. So if you're really unsure or not sure, but you are for sure that the smallest markings represents a certain amount, all you have to do is divide it by 2. And if it goes to 2 decimal places when you do that, whatever number you get, that's how far you should take the reading. If it only goes to like 0.5, means you should take it to the first decimal place. If it goes to the whole number, you should take it to a whole number. So that's another way that you could really figure out to make sure that you are given the reading to the proper number of digits. But the general rule usually works in most cases. Again, if you can figure out that smallest marking, one more place to the right is, and most times, going to be probably the correct one to do. Any questions on taking measurements? So speaking of significant figures, I think we kind of finished up talking about how to properly identify significant figures, if I am not mistaken. So I think we got some slides coming up, some of the rules. Remember that the main rules, as we talked about, any non-zero number is going to be significant, and we do count left to right when we have a number. So we go left to right, and we don't start counting significant figures until we hit the very first non-zero. So once we do, then we can count our significant figures. So obviously following this, that is our first non-zero, and then all the rest of those numbers are also non-zeros. So that would be 4 significant figures. Same thing here. That would be our first non-zero. The rest is also non-zero, so that would have 2. that would have 3. And once again, all these are non-zeros, right? We'll have 5 in this particular case. So anything that's a non-zero number will be a significant number and is important. Speaking of measurements, like we talked about, right? The uncertain number or the estimated number, right, is always the last significant figure, right? So again, as we talked about, I think last time, it's not necessarily always the last number that's written, but it is the last significant figure that you see in that number. Now, zeros are also things that give people trouble. So one type of zero, or sometimes I think we called it last time trapped zeros, captive zeros. And those are basically zeros that are trapped between two non-zero numbers. And those will always be significant. So when we go to count our significant figures, we'll start to the left. That 5 is a non-zero. So that's where we should start counting. We have these zeros here that are trapped. So they're going to be significant, along with the 8 at the end, which will be significant as well. Same deal here. We would start here. This guy is going to be trapped, so it's significant, and that one would be as well. This number has some leading zeros that we also talked about. And again, leading zeros are not significant. And we could just follow the same rule we just talked about. I would not start counting here until I got to which number? 7, right? So all those zeros come before that very first non-zero, so that I don't have to worry about those being significant. But once we do hit 7 here, again, that 0 is going to be significant, and that 2 would be significant at that point as well to get you 3. Same thing here. This 0 would not be counted as it's a leading 0. Our significant figure counting would start right there at the 4. And again, we got a couple of trap zeros along with some non-zero numbers there, which would be 5. Another type of zero, which is sometimes the most difficult for some people, is really that 0 that comes at the end. And if you remember, the 0 that comes at the end may or may not be significant. And again, what determines whether or not it is significant is there an actual decimal point written in the number? So if you're counting significant figures, I know sometimes we assume like the decimal point would be here or not. It does have to actually be written in a number when you're kind of thinking about significant figures. So if you have a decimal point written anywhere in that number, that will turn any 0 that comes at the end to become significant. If you do not have a decimal point in that number, then any zeros at the end would be not significant in this case. So in this particular case here, we have a 2. We have zeros at the end. But once again here, there is absolutely no decimal point actually written. So the only significant figure here would be the 2 in this case. Here we do have a decimal point written, which we would start counting at the 4. And then that would turn all of our zeros here into being significant in this case, which would be 4. The uncertain number and the first number is which one? The 200, which one is the estimated digit or uncertain digit? It is the 2, yes. The 2 is the only significant figure that's there, and that is the estimated digit as well. In this case, those zeros are really just kind of like placeholders to maintain it being like 200 and not just 2, right? So again, this is what I was talking about a second ago. The estimated digit in this case is actually the 2. It is not the last number that is written. In a lot of cases, it will be, but it is always the last significant figure that is written there. And in this case, it would be the 2. The estimated digit on the bottom one would be? It would be the last 0, right? Would be your estimated digit in this case. Now, obviously, that 200 minutes has a pretty wide range of error, right? You're like, I think it's 200 minutes, but who knows? Maybe I fell asleep and it's 300 minutes, right? Or maybe it's 100 minutes and that type of stuff. So clearly, the more significant figures you have and stuff like that, maybe a better measurement you would have, right? The less significant figures, not the greatest measurement probably in terms of sort of error. Zeros at the beginning, as we talked about, again, are not going to be significant until we hit that very first non-zero. So there we have 3, with that 0 being significant at the end because of the decimal point. We got the 2 there in the second one being the significant figures. And then the very last one, again, that 3 is the significant one. Once again, sometimes people go, like we talked about maybe last time, well, these zeros come after the decimal point, a reminder that we have not started counting until we got to here. So even though they do, they're still considered leading zeros going into that 3. Any questions on counting significant figures? Yeah. If it doesn't have a decimal, it doesn't necessarily mean it's like the first number or something like that, if that's your question, because I think maybe we looked at this question, which is I think used to be in the lab, and they want to know which one is the estimated digit, right? Estimated digit here is, it is the 2, right? As it says 2 significant figures. Just like if you had something like this, estimated digit now is the 3, right? And you see I'm really creative with the numbers here today. So 1, 2, 3, 4. The estimated digit here is going to be now the 4, right? And just to finish it out there, estimated digit now will be, it would be the 0, because now with that decimal point there, the 0 at the end will now become significant. Yeah. Any questions on that? All right. Again here, that's our zeros at the end with no decimal point. So again, none of these zeros here are going to be significant. So that is our 2 significant figures there, our 2 there, and our 3 there. I think we talked about it last time, but again, just to remind you that when you do write a number in scientific notation, any of the numbers that come before the times 10 part of that number are considered to be significant, even if there's zeros, because it's usually 1 point something, right? So all those numbers are usually significant. So here we would always look before the times 10 part, and we can see 4.90 is 3 significant figures, 8.0 is 2 significant figures, and 6.033 times or 0 is 5 significant figures. Now on this, sometimes people, for example, what's this say? How many significant figures would this one have? It would be 2, yeah? And you should count the significant figures as it's written in scientific notation. Sometimes people go, okay, let me just convert this out to something like this, and then maybe they'll put a decimal point at the end or something like that and go, now it's got 5. So it should not have that. If it's written like that, you should assign the significant figures based on scientific notation, what's there. I think we also talked about the idea that, again, if you go from scientific notation to really decimal form or positional notation, or from decimal form to scientific notation, you should not lose any significant figures along the way. So you should maintain it. The nice thing about sort of scientific notation and significant figures is, again, you pretty much can control how many significant figures you need when you write something in scientific notation. So for example, I have this guy here, which would have 2 significant figures. But if I needed 3 significant figures for some reason, if I was doing a calculation, I could very simply just add a 0, right? And now it has 3 significant figures. If I needed only 1 significant figure, I could get rid of the 2. And now it has 1 significant figure, right? So there are certain times when you do calculations, as I might have mentioned, as maybe we'll come across, you need to give your answers, obviously, to the correct number of significant figures. And there's really no way to do it in like decimal form. There's just no way to put a number that's not in scientific notation to get the right number of significant figures. So again, scientific notation may be the only way to really get that number to the proper number of significant figures. And again, because you could really kind of control how many you put on there. Any questions on that there? Yeah. Well, you wouldn't necessarily need to in a situation like this if you had just a number. You would want to give it. So what I mean by this is, let's just say we did a calculation and basically 6.2 times 10 to the 4 was our answer that we got like on our calculator. But when we look at the calculation that we did, we know in the end, I don't need two significant figures, but I need three. So at that point, what you could do is, again, just add that zero in there and you would have the correct number and stuff like that. So that's more often how it would probably happen. You do some type of calculation and, all right, maybe the calculator spits it to you with 6 significant figures, right, in scientific notation, but you only need 2, right? So you could trim some of that down and get it to the right number of significant figures. Other questions? All right. Again, this demonstrates what we were just talking about. We keep all 2 of those zeros because the way that is written, it has 3 significant figures. So when we transfer it over into scientific notation, we want it to still have 3 significant figures. That is why we would not write it like this, because writing it like this has how many significant figures? 1, right? So now we just lost 2 significant figures, and it's the same thing as taking measurements. We just made that number a lot crappier than it should be, right? So we don't want to do that. Same thing here. In this case, the only significant figure is the 4 in this case, right? None of those zeros are significant. So when we do turn it into scientific notation, we would drop the zeros in this case, and that way it will maintain at 1 significant figure. It's really the same reason as why you would not drop the zeros. You would not add the zeros, because if you did it like this, what is that to 5? How many significant figures does it have now? That's a lot of numbers. Yeah. So that let's go with the one that I underlined. So that is 2, 4, and 6, right? So it now have 6 significant figures, which just made it not crappier. It made it a lot better than it should be, really, right? It shouldn't be that good of a measurement. So just like you shouldn't drop them if you should keep them, you shouldn't add them if you should drop them. So it works both ways in terms of that. Our last one here, the 0.30, has 2 significant figures. So again, when we translate it over there into scientific notation, we want to make sure we keep 2 significant figures. Yeah.
Are we ever gonna have to deal with numbers like the first one, with this decimal point? And, obviously, like they should put a 0 behind it.
Well, they maybe shouldn't put a 0 behind it, because if they did, then it would have 4 significant figures, right? So it could be really determined by how they took that measurement. That truthfully, as far as they could go, really is kind of like the whole number there, the first, the ones place. So there might be a reason why really they didn't put the actual 0 there. Because written like this, right, with the 500 and the decimal, the estimated digit, right, is that last 0. And that's where the uncertainty would lie, right? So by writing it like this, what you're telling somebody is, I think it's 500, but maybe it's really like 499, right? Or 501. Kind of the uncertainty is kind of in that place of it. So again, it may not seem like a big deal if you inserted the 0 in there, but now the uncertain number would be which one? It would be the last 0 in this case, right? And what you're telling somebody if you reported it like that is, I think it might be, maybe 499.9, right? Versus 500.1 or something like that. You're telling people, I think the error is way over here in the 10th place rather than, the ones place, which means this would technically be a much better measurement than this one, right? So based on the equipment, you may not have that ability to do that. So that's why they leave it off. So you may come across numbers that look like that for that reason. Other questions? Yeah. You said this number here? Yeah. Yeah. Uh-huh. So if we want to turn this into scientific notation, because it does, you would actually keep all these zeros, and it would be 4.00 times 10 to the 1 in this case. Yeah. And that will get you your 4 significant figures that match the 4 significant figures that you have here. Yeah. Other question? Yeah. All right. Identify significant and non-significant zeros in each of the following. write them in scientific notation. All right, so why don't we do how many significant figures in each of these, which ones are significant, and then write proper scientific notation with the right number of significant figures. I'll spit that out maybe. Okay, let's take a look. So look at the first one. Let's start with how many significant figures are there? There are 4 significant figures. We are not going to count these. This is where we're going to start to count. The 0 at the end will be significant because there is a decimal point in that particular number. Remember that when we write it in proper scientific notation, again, it needs to be a number between 1 and 10, not 10. So we have to move the decimal place in this case 1, 2, and 3 places. That gives me 2.650 times 10 to the minus 3, as that's a small number, should be a negative exponent. I need to keep all those digits, right? Because now it still has 4 significant figures each way. Yeah. Questions on that one? Yeah. It's -3 because when you move the decimal place to the right, turning it into scientific notation, it's a negative exponent. The easy way to remember it is that's a small number, right? So small numbers should have negative exponents. Yeah. Other questions? All right, so this guy here next in B has 5 significant figures. We would start here. The only 0 we really have is one that's trapped between 2 numbers, which would make it significant. Here we actually need to go 1 place to the left to get us a number between 1 and 10. That is 4.3026 times 10 to the 1. We went there, grams. Again, we need to keep all those numbers because that is how many significant figures we got going on. Lastly, here C has how many significant figures? It is 4 significant figures starting here, moving this way. These are not going to be significant because there is actually not a decimal point written in the number. But to help us move it into scientific notation, at the end there is where we assume the decimal would be, right? So we would go 1, 2, 3, 4, 5, 6, I think. And this would be 1.044 times 10 to the 6th. I scribbled over it. I think it's a liter that's behind that. And again, that would get you your 4 significant figures. Any questions on any of those there? Yeah. Yes. So I think your question is this. So if you have a number that is not in scientific notation, so sometimes called positional notation or decimal form, whatever you want to call it, you have a regular number, you want to put that into scientific notation. If you move the decimal point to the right, it will end up being a negative exponent. And if you move it to the left, it will be a positive exponent. If you are already in scientific notation and you need to put it back to like decimal form, it is opposite of that. So in this case, the negative, if we wanted to put it back into here, we would actually go to the left. Yeah. So it is sort of opposite if you go in the opposite direction. Like that. So like I said before, probably the easiest way to remember it is if you know it's a small number, negative, and if it's a larger number, basically it should be a positive. Yeah. In terms of moving yeah, so it's almost kind of 2 separate things in a sense. In terms of significant figures, if you were just strictly counting significant figures, the decimal point has to be written for you to count those zeros. But the normal rule of thumb is, right, if there is not a decimal point written in a number, it's assumed to come after the very last number. So you kind of have to do that to move your decimal place to the proper number of digits for scientific notation. Other questions? All right. So hopefully they agree. Oh, that's good. I'm not going to look. I'm just going to hope they agree. All right. So a lot of what we've been talking about, obviously, with significant figures and measurements are a type of numbers which are sometimes referred to as measured numbers. And obviously, these are things that are typically achieved through a measurement. There's another type of number that we sometimes come across in chemistry, and there's really kind of two ways that we sort of come across these numbers. And these are what are referred to as exact numbers. And really, exact numbers are found really one of two ways. For example, if I had, these pens on my desk, right? And I wanted to know how many pens I have on my desk. I'm not going to do some type of experiment to figure that out, right? I'm just going to simply count them, right? So one way that you could get sort of an exact number is anything that's counted. The classic textbook example is like you got apples in a barrel, right? You just kind of count, or a basket, you count the apples, how many you got going on. More commonly, the way that we sort of come across exact numbers in chemistry is there are also definitions. And by definitions, what we mean are equalities. And equalities are basically two things that represent the same amount of something, but they're on different units. Like if I have $1 and 100 pennies, that's the same amount of money, right? They're just different sort of units or different sort of ways. So something like this, for example, 1 foot is 12 inches. That is a definition, and that is considered an exact number. 1 kilogram is 1,000 grams. That is also considered an exact number. Now, the deal with exact numbers is, for the most part, they can pretty much have as many significant figures as you want. The one place where we come in contact with sort of exact numbers that we need to kind of think about them, or maybe not think about them, is when we do calculations. So when we do calculations, we want to give our answers to the proper number of significant figures. If you come across a definition that's considered an exact number in like a calculation that you do, you don't have to worry about it at all. So you don't have to worry about, it's not going to have any effect on your answer and how many digits you should give in your answer or anything like that. So we sort of ignore exact numbers and calculations in the sense of helping us decide how far we should take our answer to, how many digits, because they technically can have as many as you want. So I may say, hey, it's got 4. You may say it has 3. And because there's that, like, it can have as many as you want, we sort of take it out of the equation when we actually do calculations. Now, there is an important distinction and difference in terms of a definition that you should really just ignore and consider an exact number, and one really that you should sort of look at and take into consideration. And that has to do with the two different types of units that we talked about. If you remember, there are like the English units, right? And there are really the metric sort of units, right? And if you're going to be using any type of English sort of conversion, like for example, 1 foot is 12 inches, that is considered an exact conversion. So that's considered an exact version. You don't have to worry about the sig figs that are going on in that conversion when you use it. If you use something that is a metric to metric conversion, like the bottom one there, 1 kilogram is 1,000 grams. That also is considered to be an exact conversion, so you don't have to worry about it. It is only, typically speaking, if you use an equality or conversion factor that jumps between those two units, that is like an English to metric conversion or a metric to English conversion, that you do have to take into consideration the significant figures that are present when you're doing a calculation. And we'll talk more about that later when we do some calculations. There are some exceptions, though, for like the English to metric sort of conversion. The most common one is the 1 inch is 2.54 centimeters. That's an exact conversion. So although it does cross over from English to metric, you don't have to really worry about it in that sense. For example, if you had something like 946 milliliters is a quart. That's like a metric to English sort of conversion. In this case, we would want to look at the one that's actually a number, not the one, but we would want to look at 946. And if we were doing a calculation, we would go, okay, that's got like 3 significant figures. So I got to take that into account maybe when I give my final answer. So there are a few English to metrics that are exact. That's exact up here. Some people, and I don't recall what your book uses, but some people will use for a pound conversion is 453.6 grams. That's an exact conversion. But some books and some people will use the sort of non-exact conversion, which is 454 grams. So if you chose to use this as a conversion factor, that is not an exact conversion between those two. And you would have to take the 454 into account as having 3 significant figures when you're doing your calculation. So I would say almost in a lot of cases, what we'll come across are ones that you probably could just go, seems exact to me, we're okay, you know. But there are some, just so you know, if you cross over that metric to English sort of conversion, there are places where you do need to kind of take that into account. Otherwise, you could sort of ignore those in terms of helping you decide how much your answer should be. So here are some examples. Again, 8 donuts, 2 baseballs, 5 capsules. Those are all things that would be counted. Obviously, on the middle there, all metric system sort of conversions. So those would all again be considered exact numbers. And so with our English or US system there on the right, be considered exact numbers. All right, so let's take a moment here. Are each of these measured exact? And if they are measured, how many significant figures are there? Okay, let's take a look. So first off, the 3 coins here should be measured or exact? It should be exact. Diameter of a circle is 7.902 it is measured. And how many significant figures does it have? It does have 4 and 4. And 60 minutes is 1 hour is exact, yeah. By the way, there's how many seconds in a minute? Right, how many hours in a day? 24, right, not 60, by the way. That's a common mistake people make on exams. They go 60, 60, 60 hours seems like a good day. All right, state the number of significant figures we got going on here. So let's take a look. 0.030 would have 2 significant figures, being these 2 right here. 4.050 would it be 4? Sounds good. 0.0008. It would be 1. Again, all these zeros would be considered leading zeros because we would not start counting until we hit that first 8, which is our non-zero. And lastly, here we would have 3. Again, the 0 here is significant because of the decimal point you got going on right there. Any questions on any of those? All right. Glad they agree. All right. All right, so why don't you go through this? I guess pick the one that matches. All right, let's take a look. Starting with the first one, which of the answers there contains 3 significant figures? It is 2. Again, these 3 would be significant as we would start counting up to 4. This guy has 4 significant figures, right? And this guy also has 4 significant figures, right? So 2 would be the correct one. All the zeros are significant here. Which one? 2 and 3. Yes. These are not significant, so that eliminates that. These will be significant because of the decimal point. And all these are significant because it's written in scientific notation. So in this case, it is 2 and 3 as a winner there. Lastly, a number of significant figures there in 5.8 times 0 times 10 to the 2 is 3. There we go. Any questions on identifying significant figures? All good. Professionals, I like it. Sounds good. All right. Then let's talk about probably also a really important thing, which is a calculator. person has gloves on using the calculator. All right. So I guess they're in lab. I suppose that's why they have it. So let's talk about when we do calculations and significant figures. So we do always want to kind of give our answers to the proper number of significant figures. And there's really, for the most part, there's really sort of two sets of operations that we typically will do. We typically will either multiply or divide. And when we are doing any type of calculation where we are multiplying and dividing, our answer should end up with the same number of significant figures as the one with the least number of significant figures. So our answer should have the same number of significant figures as the number with the least number of significant figures. So if I were to take 3.20 and times it by 1.2, this has how many significant figures? 3. This number has 2. That means my answer should end up with how many significant figures? 2 significant figures, yeah. So if you did that on your calculator here, 3.2 times 1.2, we end up with 3.84, right, on our calculator. The correct answer here then should be 3.8. Yes. That 4 means we just drop it off in this case, and we'd end up with that. Now, the other sort of operation that you typically will do is add or subtract. And when you add or subtract, your answer should have the same number of decimal places as the answer with, or the number with the least number of decimal places. So when you add and subtract, it is not significant figures you're looking at. It is actually decimal places, and it's the least number of decimal places. So your answer should have the same number of decimal places as the number with the least number of decimal places. So if I take a number like 1.111 and I add it to 2.3 and I add it to 4.12, let me give it the old college try without the calculator. We'll do that. That's maybe a 3. That's a lot of fingers I need there. That's like 5, 6, 7. I hope. There you go. 3, 4, 5. All right. I think I did good. Don't look too closely, but I think I did all right. So here we are adding this together, and we are looking here at, again, decimal places, not significant figures. So if we look at decimal places here, this guy's got 3 decimal places. That one has 1 decimal place. That has 2 decimal places. That means my answer should end up at, it should end up at 1 decimal place here, and we should end up at 7.5 in this case. 7.5 does have 1 decimal place. How many significant figures does that have? It does have 2, which are 2 different questions, by the way, yes, and may also be important if you take that number and continue on with the calculation to do something else. So make sure you keep that in mind. So adding, subtracting, you're looking at decimal places. It's the least number. Multiplying, dividing, you're looking at significant figures. It's the least number. It is the least number in both of them because, frankly, your calculation, your measurement is only as good as your crappiest measurement, which would have the smallest number of significant figures, the smallest number of decimal places. Those are your worst measurements. So you could only be as good as your worst measurement. So that's why we look at the least one, kind of like, you're only as strong as your weakest link, right? So your least one is your weakest link in terms of your calculation or measurement that you make. Any questions on the difference? Yeah. You want me to read your math? I want to try. That. I didn't use the calculator. I didn't even use my fingers. I was proud of myself. I was going to use my fingers, but so if we change this, so I'll just rewrite over here. So we did 1.111, and you're going to add it to 2 and a 4.12, right? So let's try that again. So that's a 1, a 3 now. That's up 2, and a still 7, I think, in this case, right? So the smallest number of decimal places in this case is no decimal places, right? So whole number. So you would, as you said there, just the 7 in that case, yeah. And again, that's because in that grouping of measurements there, if those are measurements, the worst measurement out of the bunch is which one? Is a 2, right? You're saying basically, I think it's 2, but maybe it's 3, maybe it's 1. That's a pretty big range of error, as opposed to the first one where you're saying, I think it's 1.111, but maybe it's 1.112, right? Or 1.110. That error is way over there, right? So much smaller room for error. So that's why it would be that bad. Yeah. Yeah, it's straightforward like that. Is the least number of decimal places. Yeah, don't overthink it. It definitely is the least number of decimal places, and it's the least number of significant figures. So the important part of this is to keep those two straight, right? So sometimes people start going decimal places on multiplying, dividing, and significant figures on the other. Or some people just roll sig figs on everything because it's like in your head for everything that we've been talking about, right? So sig fig seems like a good idea for everybody. So significant figures, decimal places, they are both the least number in each case. Now, you do also want to keep in mind that if you're doing multiple steps along the way, you got to kind of keep track of what you're doing. So, for example, let's say we were going to do 1.2 times 3.220 divided by 420.5, and we're going to equal here. Yeah. Now, if I'm going to do this math process here, right, I typically would start with which part of it? Yeah, the stuff in the parentheses, right, is where we would start. So on the top there, we're multiplying, right? So we're going to be looking at significant figures in this case, right? So the top number here, technically speaking, this guy has got 2 significant figures, right? This one has 4 significant figures. So technically speaking, when I get an answer for the top part, it should have technically how many significant figures? Should have 2 significant figures up on top, right? When I get that answer on top, the next thing I'm going to do is take the number that's on top and we're going to divide it by the number on the bottom, right? So that's still division, which means we're still looking at significant figures. So I know I should have 2 significant figures on top. My bottom number has 4 significant figures. So really the very last sort of the math thing that I did is I took a number with 2 significant figures, right? And I divided it by a number with 4 significant figures. That means my answer should have how many significant figures? Should have 2 significant figures along the way. Yeah. First off, any question on that there? So if we were really to do this calculation, we want to talk a little bit about rounding like it shows there. You really don't probably want to round in most cases until kind of the very end of the calculation. You should definitely keep track of what's going on in terms of significant figures, decimal places, depending on what you're doing. But you really don't want to round kind of till the end, especially if you're doing a multiple sort of step calculation. If you kind of do the first step, get an answer and round it really strongly and strictly, and then take that number, do the next calculation, and then round that one again, and then kind of keep doing that. Every time you round it, you will move yourself further and further away from the correct answer. So it's a good idea not to round to the very end, but you do need to sort of keep track of what you're doing so that you could clean it up in the end. Do you need to keep all the numbers? You don't, but you should keep a good couple of numbers or so past where you should lay it up. Yeah. So for example, on the top there, if I took 1.2 times 3.220 and I hit equals, maybe there we go. We end up with up on top here in this example, 3.864. Now, technically speaking, right, that top number should be two significant figures. I personally would not take it to 3.9 at this point and around it, because I still have a little bit more math to do, right? So what I want to keep in mind is, all right, well, technically that should be two significant figures. And personally, if I was to do it, I would just take the whole number that's in my calculator, and then I would divide it by the bottom number, which is 420.5. And this is going to give me on my calculator a big number here, 0.0091896061. Now, you should not give me a number like that or more numbers, right? Because that's not good either. But at this point, I really didn't round anywhere along the way. I kept all the numbers, and that's going to probably keep me really close to what the real number really should be. Now that I'm done with the calculation, I could go back and sort of think about, where I should end up. So we would do kind of what we did at the beginning here. Okay, I know the top guy should end up at 2. Now I'm taking 2 significant figures divided by 4. So now I should end up at 2 significant figures. So now I'm going to come to my number here. And now I'm going to round it to the proper number of significant figures. And by the way, with the 8 next to me, I should round up, right? So this should be something like this, yeah, which would be 2 significant figures. You could also, if you wanted to, write it a little scientific notation action like this, which would also be 2 significant figures. But you really do want to sort of avoid rounding until you're sort of at the end, but you should definitely keep track of everything. What usually will determine a lot of times where you end up is you want to really follow the sig fig rules the same way you did the problem. So for example, here I did the top part first, and then I divided, and that was my last step. So that's going to help me really determine where I should end up. First off, any questions on that there? Yeah. Mm-hmm. I wouldn't do 3.9 divided by 420. In this particular case, it may not make a tremendous difference. But outside of these sort of significant figure type questions, when we do real calculations and you're doing some type of calculation and you're going to get an answer and then take that answer and do another one, it's really good practice not to round until really the end of it. And the reason for it is if we're not doing a ton of calculations here in this particular problem. But if you round really strictly on every single step along the way and say like a 3 to 4 step calculation every time you get an answer, you're really losing a lot of where the answer should be. You're really making it too you're taking away a lot of the sort of error in it. So you'll end up yourself kind of far away from the correct answer. So try not to round to the end, but you should definitely keep track of everything. Sometimes people refer to it as not rounding in the middle, keeping like a guard digit or 2, and you can put a little line sometimes above it if you want to do that. Yeah.
So that's 4 significant figures. When you divide by 420.5, that's 4 significant figures. How come your answer can't be in 4 significant?
It really shouldn't be 4 significant figures, because although I did keep it at 3.864, which is 4 significant figures, I kept it that way so I didn't end up with some rounding error. Yeah. But I know in my head, although I did write 3.864 there, that really that thing should be 2 significant figures. So that's what I was saying. You really don't want to kind of round really strictly until really the end, but you do need to keep in your head kind of what it really should be, and that's why you typically will kind of clean it up at the end. Yeah. Other questions? Now, yeah. Well, it's really based on the calculations that you did and really where you kind of end up. So, as we did here, we first multiplied, right? So we got to think about what we should end up with in terms of sig figs on that. Then the next step that we did is divide. So we still need to think about significant figures. Now, for example, if we did the same one here, we'll do 1.2 times 3.220. divided by 420.5. Now let's just say at the end here, we're going to add a number to it, like 3.2 or something. All right. So at this point, right, we already know that if we go through the whole math, I think this is the number we hit right on our calculator, if I'm not mistaken. So we really have this number here, right? Which at this point in time, we're going to then add, right? So we've taken care of all sig figs to get the number on the left. We know in our head we should end up on the number on the left at how many significant figures? 2, which is technically here, right? But now the very last operation we're going to do is adding, which means should we be looking at significant figures? We should be now looking at decimal places. So this is why it's important before we move on to the adding step, which is the last step, that we understand that I should end up at 2 significant figures, which is important because with 2 significant figures, now that I'm adding, this number here should have how many decimal places when I add? It will technically have 4 decimal places, right? If we were to stop there at the second significant figure. And that's important because when I now take this number and add it to this number that has 1 decimal place, how many decimal places should we end up with? 1. So when we take that number, and again, I could take the whole number here, or at this point, if you wanted to, you could round and take the 0.0092 number if you wanted to, and then add it. When you add it to the 3.2, you end up with basically 3.209189061, which means we should really end up with 3.2 in this case, right? Which has 1 decimal place and how many significant figures? 2, yeah. So in this case, because we had that additional step, which was the last step that happened to be addition, now we have to switch from, okay, we're going to put this number together with this number. We got to look at decimal places in each of those. So you always got to kind of think about significant figures and where you should end up the same way as you kind of do the math part of it. Yeah. So, okay, I'm going this way. This is adding, multiplying, dividing. I'm looking at sig figs. Then maybe I'm going to take this answer and add it. Now I need to switch over to, that's the last step I did, was look now at the significant figures, but I'm sorry, the decimal places, but you still have to take into account the proper number of sig figs on that multiplying and dividing part like we did here. Any questions on it there? Okay, now let's take the square. No, I'm just kidding. No, that's not. Okay, let us continue on. So we've been talking about rounding. We've been talking about rounding, and let's talk about the official rules for rounding. As we've been talking about, again, if you're doing multiple step calculations where you may get an answer you want to continue on, as we've been talking about, try to avoid that rounding to the very end. If you want to do calculations all in one step, you can, but if you are going to do multiple steps, that's fine too, but just watch that rounding. Did you have a question? Yeah. Oh, come on. You want to drop to zeros because they're sort of placeholders. If you drop to zeros to just, are you asking just drop to zeros to like 91 or something like that, or 92? Or? To 9.1. No, because there's a very big difference. Again, just like sort of rounding zeros off of the back end or something like that, you don't want to round them off the front end because there is a really big difference, right, in the meaning of the number of, say, 9.2 versus this number, right? There's a big difference in what that value means. So because the real value there is definitely under 1, right, basically. 9.2 is way over 1, right? So there's a really big difference in the meaning of that. So that's why we would not get rid of those zeros at the front, because they're sort of placeholders to hold it to the right sort of value. Yeah. Good. Yeah. Other questions? So we could have, if you wanted to, like I said, you could have just rolled with this number here where you rounded it to where it should be with the right value. And then you could have added it to the 3.2. And really you would get basically, get that, right? But in the end here, we're still doing what we talked about at the very end, which is the very last step that we did in this calculation is adding, which means we should look at decimal places. And that 0.0092 still has 4 decimal places. And that 3.2 has 1 decimal place. So it should end up there at that 1 decimal place, which in this particular example ends up at the 3.2. Yeah. All right, so when we do round, normal rounding rules apply. So if wherever you need to lay up your sort of number in terms of significant figures or decimal places, you always want to look to the number to the right of that, right? So you go to wherever you really should end your measurement or calculation, you go to the right. And if to the right is 4 or less, you pretty much just drop off those numbers. And if it's 5 or more, you do go higher than that, right? So for example, again, if I had 14,432 and I wanted 2 significant figures, the answer should be 14. Everybody agree? 14 has how many significant figures? Yeah. All right. So if I owed you $14,432 and I said I'm going to pay you 2 significant figures, here's $14. Are you going to be happy with me? You look like nice people. Maybe you'd be happy with me, but there is a tremendous difference, kind of like we were just talking about. There is a tremendous difference between the meaning of 14, right, and 14,000, right? So it's a very common mistake that people make is that they're very focused on giving the right answers to the right number of significant figures. They do what I call extreme rounding, yes, and they just like, I got the right number of significant figures for sure. So you never ever want an unhappy face like that, right? But you do not want to really change the meaning of the number by rounding. The right way to do it would be something perhaps like 14,000. Yes. Now, if I give you $14,000, you don't feel so bad about losing $432. I get a teacher discount. It's a good thing, right? And it kind of means the same thing, right? So in the effort of getting the right sig figs, which you should always do, people very commonly go way too extreme on the rounding. And that's also why we don't want to round in the middle of a calculation, just in case you go too extreme. That's going to screw up the rest of the calculation very badly, right? So that's why we do sort of keep some extra numbers along the way, so we don't have that impulse of incorrectly rounding maybe as well along the way, that we definitely would move away from it. By the way, the another way we could write this, right, is 1.4 times 10 to the 1, 2, 3, 4. That also would have 2 significant figures. Could I put a decimal at the end of the 14,000? Can I do this? Would that be correct for 2 significant figures? It would not, because with that decimal point, now those zeros at the end are significant, and now you got 5, and you go back to the unhappy face, which you don't want, right? Now, again, as we've been talking about, sometimes there really is sort of only one way to get a number to the proper number of significant figures. So for example, here, let's just say I had 12,000 and I wanted 3 significant figures. Is there any way to write it in decimal form and still have 3 significant figures? Yeah. Yeah, but without scientific notation, is there a way to do it decimal form way? There is not, right? Because you put a decimal at the end, you now got 5, right? You put a decimal after the first 0, you now have 120, which goes back to that is not the same thing as 12,000, right? So you just change the meaning of it. And by the way, if you drop those zeros, you still have 120. So really, again, as you correctly said there, really the only way to properly get this into the proper number of significant figures would be to write in scientific notation. So this is what we were talking about earlier, that in certain cases, when you do a calculation, you get to the end and go, oh, that number is not going to work very well in like decimal form to get it to the right number of sig figs, but I can definitely turn it into scientific notation and get the correct number of significant figures. Any questions on that there? All right, so no extreme rounding. All right, so here's just some examples. 8.423, we're going to go 3 significant figures. So again, we will drop the rest of them. Now, in this particular case, just to remind you, you may be again wondering, can I just turn these guys into zeros instead of dropping them in this situation? And if I do turn them into zeros, do I have 3 significant figures? I do not. So in this case, this is why we do need to drop them, right, to get to 3 significant figures in this case. And there's the 14.78. So we would look at the 8 that's next door. It's above 5. Here we would round up and end up at 14.8. And for 3256, we would go here. We would look there. We would round up to give us the 3260. Here we do not put the decimal point again at the end there because we would then end up with 4 significant figures rather than 3 in this particular case. And this obviously shows you if you want to go down to like 2 significant figures, what you would end up with. All right, so write the correct value for this guy here, 3.145. Okay, so taking a look here, we're going to first go to 3 significant figures. Once again, we are going to start counting there. So our 3rd significant figure would be the 4 in this case, right? So we then need to look to the number to the right of that. And in this case, it is a 5, which means we should round up to do that. And we should end up with 3.15. Thank you. It's getting late. It's been a long day. So that is a 5 there. And that would be 3 significant figures. Now, if we want to go to 2 significant figures, we'd do the same thing, but our 2nd significant figure would actually end us at the 1 in this case. We would do the same thing. We would look to the 4 that's next door, and the 4 next door means it's less than 5. So we're just going to drop the rest of those numbers, and we will end up at 3.1 in this case. Yeah. Any questions on those there? All right, justifying calculated answers to give 3 significant figures correctly. Okay, so as a peek here, this we're looking for 3 sig figs off the rule. These are some maybe answers that you got on your calculator. Also a good reminder, right? Your calculator does not spit out your answer to the right number of sig figs in most cases, right? So you do need to analyze it, maybe get rid of some numbers, maybe add some numbers and stuff like that. Also, I think we talked about it with scientific notation. It doesn't usually give you your answer maybe in scientific notation unless it runs out of room or unless you have a program to do so. So just keep those in mind. 3 significant figures starting at the 8 would take us to the 4. We look at next door, which is a 7. So we're going to round up here. So that's going to be an 825 centimeters, right? Here, we don't start counting sig figs till we get to the 1. That means our 2 would be our 3rd significant figure here. That would be 0.112 in this case. Now, in this case, that is our 1st significant figure. That's our 2nd significant figure. What should we do? Add a 0, right? So anyone in doubt there, we'll add a 0. Now we turned it into 3 significant figures. That 0 again would be significant because there's a decimal point obviously in that number. So that all works out okay. Any questions on any of those there? Yeah. Stuck on.
Because it says 3.
Mhm.
You just add 0.
For which one? B? For B? The point 1, 1, 2, 1, that way? Yeah. So when we look at this number, so when we're counting significant figures, this is not significant because we haven't hit the first non-zero. So we don't really start counting until we get to that guy, which means the 3 significant figures would take us to the 2. And then we need to look at that guy right there. And that's why we dropped the rest of them. Yeah. Yep. Other questions? All right. All right. So we sort of went over this a little bit earlier, but here's the official slides. But just to review again, as we talked about multiplying and dividing, we are looking at significant figures. So here, as you can see up there, we basically have 2 significant figures times 4 significant figures, which means up on top, we really should have 2 significant figures. The next thing we would do would be to divide. So we're basically dividing 2 significant figures by 3 significant figures, 2 significant figures there on the outcome of that calculation. Here again, adding, same idea when you put this, or not, I guess it's not really adding, or adding significant zeros, I guess I should read it, but we're dividing here. So we are looking at significant figures here. So this is 3 significant figures up on top. This is 3 significant figures on the bottom. Once again, your calculator will not give it to you necessarily in the right numbers. So here we would need to add those zeros, right, to get us to 3 significant figures, which is what our answer should be. If we just wrote 4, it would have 1 significant figure, right? Which would be incorrect in this case. By going 0.00 and adding those zeros, it gives us the proper number of significant figures, but it doesn't change the meaning, right? 4 and 4.00 is still 4. So it's the same meaning of that number, even though we added some zeros, but it does give us the proper number of significant figures when we look at it. All right, so here, if we were to do this, we're going to take 5 times 3.408. We're going to hit equals. We're going to divide it by 2. And frankly, this is how I would do this problem. Not really worry too much about significant figures at this point. I would get an answer of 8.52, right? Centimeters, by the way. At this point, what I would want to do now is sort of analyze my math, right? Because this is basically what the calculator spit out to me, which may or may not be correct. So again, here we're multiplying on top. So we have significant figures we want to look at. That is 3 significant figures. That is 4 significant figures. Top guy should end up at 3 significant figures. We're then going to divide now, right? The top number by the bottom number, which means we are still looking at significant figures. So we're looking at 3 significant figures divided by 2 significant figures. That means my answer should end up at 2 significant figures, which is here, 8.5 centimeters. Yes. So again, you can roll through the calculation, but you do need to kind of take a step back and sort of figure out what you did mathematically so that you could get your answer to the correct digits. Any questions on that there? All right. Hey, there we go. I don't think that is right.
Back to the last slide, I do have a question. Let's say the top number comes out to be, let's say the bottom number was 3 significant figures and the top one. Let's say the answer ended up being less significant figures than what you already have.
Okay.
Would that mean that the significant figures has to be that many that the answer was?
So let's just say that we had 5 times 3.408 divided by 2. So I think this might be what you're asking. Yeah, something like this. Okay. So if we do this mathematically, we're gonna get the same number, right? 5 and 5.00 is gonna give us the same number at the end, right? But now, because of the way this 5 is written, this now has 1 significant figure, right? This has still our 4 significant figures. Now, when we do the top part, we should actually end up with 1 significant figure, right? Because of that. So now when we divide that 1 significant figure by the 2, which I think is what you're asking, right? We should end up with 1 significant figure, which in this case would then take us to the 8, right? And now we would need to round up in this case, right? And then it would be 9. Other questions? Yeah. They are wrong. I was just about to say that before we went back. You are absolutely correct. I took a look at mine thinking maybe I was wrong, but I think it's a book. You can't trust books, right? Well, I know. But you are absolutely correct. They have like cubic centimeters, I think, which is totally incorrect. Unit wise, right? We basically have centimeters on top and centimeters on the bottom. They cancel each other out, right? And that leaves us just 1 centimeter that's left over. Units cancel each other out just like numbers do. So if you had 2 divided by 2, that equals 1, right? So if you have centimeters on top and the same unit on the bottom, that basically equals 1 as well. So they cancel each other out that way. And that's how the units cancel. So you are absolutely correct. I was just about to say that before we turned back. That should be maybe something like that, I think is what it should look like. Yeah. Other questions on that? All right. Adding, subtracting, again, as we talked about here, we were looking at decimal places. So adding these together, going under the assumption that they added it right, hopefully, we get 66.102. We got 3 decimal places, 2 decimal places, and 1. So we do need to go to 1 decimal place there. The next number being a 0 means we're just going to drop the rest of them, giving us 66.1, which is 1 decimal place. How many significant figures though? 3, yes. And the estimated digit would be the 1. Yeah, that's wrong. So again, if we were going to do something with that number like multiply or divide, then that 3 significant figures again would come back into play, although we did the addition part correctly to the decimal places. All right. All right, so let's try this one here. We're going to add this guy together here, 82.409 plus 22. That's going to give us 104.409. Once again, here we are adding, so we're looking at decimal places. So that is 3, that is 1, which means that is where we should end up right there. And that means we should look at this guy and get rid of it. And that's going to be 104.4, which again has 1. Should also include the units to be chemistry like. There we go. Which is 104.4. No, I didn't take chemistry. How would I know? 104.4 milligrams. And again, it has 1 decimal place, but 4 significant figures in this particular case. They agree, so that's good. Any questions on calculations involving significant figures? Yeah. So again, the 2 things you just really want to watch out for that's very common mistakes that people make is that extreme rounding and not kind of following your calculation through to follow what you should be doing with significant figures and decimal places. So don't overcomplicate it. If you're doing multiple step calculation, just start the very first part of your calculation and just keep track of sig figs to decimal places to sig figs, whatever it may be. And really by the time you get to the end part of your calculation, you should just do that last rule, whatever it is, decimal places or sig figs, but you need to have that understanding of how you got there, where everybody should be. Any questions? All right, we're going to talk about prefixes and equalities. Prefixes are used with metric numbers to change the meaning of them. Equalities, as we'll talk about a little bit later on, are basically 2 things that represent the same amount of something. So I think we mentioned it earlier. 100 pennies is the exact same thing as having $1, right? They both represent the same amount of money. And as we will talk about a little bit later on here, with any equality that you have, you basically can use them and write 2 conversion factors. And conversion factors are really just fractions where you could go 100 pennies over $1 or $1 over 100 pennies. And we use conversion factors to help us really, as silly as it sounds, do conversions, but help us really go from one unit to the next, basically. And as we'll talk about a little bit later on here in this section, we do it through a process known as dimensional analysis, which is a way that you set up calculations where you can see the units and you can see them canceling. and you know what you end up with. So for example, when you have two conversion factors like this, you would only use one in a calculation, because if you use two in a calculation, you undid your calculation, you basically reversed it. So when we have something, say like a pretty straightforward problem of, I have $5 and I want to know how many pennies that would be, right? So one very sort of common rule of math is pretty much opposites cancel. So if you want to get rid of something in math, you do the opposite sort of approach, which means if you have two numbers you're multiplying, you want to get rid of one number, you divide one number, right? If you're dividing two numbers, you want to get rid of one of them, you multiply one number, right? So you kind of do the opposite. You have a number on this side that's being added, you subtract it to the other side, right? So in math, opposites basically cancel each other out or sort of fix things. And it's the same thing when we do sort of these type of calculations. If there is a unit we want to get rid of, we put that exact same unit in the opposite location. And it's pretty simple. This approach is like they're either on top or they're on the bottom, right? So if this unit's on top, to get rid of it, we would put it on the bottom. And if we want a certain unit to end with, we would put that unit up on top so that we end with the unit that we're looking for. So for example, if I were to take my $5 here and I were to set it up that I wanted to get rid of it, and I want to end up in pennies. Although it is not written as a fraction, you could think of it as being over 1. And what that tells you is the units of dollars are up on top, which means to get rid of it, I need a conversion factor where dollars are on the bottom. And my two options here are either this conversion factor or that conversion factor, right? And I could clearly see that in this conversion factor, dollars are on the bottom, right? Which is what I want. And nice for me, up on top there, that unit is pennies, which is what I'm looking to end with, right? So that's going to be really good for me. So I would use my conversion factor like so. $1 on the bottom, 100 pennies up on top. Now, what we're going to be doing mathematically here is anything that's on the top gets multiplied. So we're going to multiply anything that's on the top, and anything that's on the bottom gets divided. Yeah. So basically anything that's up on top, we can multiply. Anything on the bottom, we could divide. So really in this particular case, we would take 5 times 100 and you pretty much would be done. But you can divide it by 1. It's not going to change because we're dividing it by 1. But technically that would be the math that you do. This would give us 500 pennies. And this is what is sometimes referred to as dimensional analysis. That's because the dollar unit up on top, when you divide it by the dollar unit on the bottom, equals 1. They essentially cancel each other out. There is nothing canceling out the pennies here, right? And that is why the unit stays. So now I just converted from dollars to pennies in this particular case. That's a straightforward, simple example of dimensional analysis. We'll obviously do some more a little bit later, but that is sort of where we're going with equalities and conversion factors, is this type of calculation where we basically get rid of units we don't want, and we use conversion factors to get to units that we are looking for. By the way, we just did some math here, right? So we should be thinking about significant figures. I just did 2 types of calculations. Basically, I multiplied and then I divided, right? Which means I should be looking at significant figures, right? Now, I do have this guy right here, which is a measured number or an exact number in this case. It is an exact number, right? Because as you know, 100 pennies exactly equals $1 of money. So that's an exact conversion. So that would be considered in this type of calculation an exact number, which means we don't even have to consider it when we're thinking about what our answer should be in terms of significant figures. So that means in this case, really the only number that we have to consider is the very first number, right? The very first number has how many significant figures? So my answer should have, and my answer has, I got lucky there. That ain't bad. So that's pretty good. So it does have one, which is again here why I would not want to put a decimal point at the end, right? I would not want to jazz it up by putting 0.00 at the end to make it more scientific-y, right? Or anything like that. Because again, I would have the wrong number of significant figures. Any questions on that there? Okay, so let's talk a little bit about some of the prefixes that we use. And a lot of times we'll use some of these prefixes as really conversion factors as well. And a lot of times people will sort of incorrectly use these prefixes, and we'll talk about how to correctly use it here in just a second. But there are some that we do come across a lot. So kilo is a very common one. So 1 kilometer is the same as 1,000 meters. And this is an equality. That is two things that represent the same amount, but are on different units. From this equality here, we could write two conversion factors, 1 kilometer over 1,000 meters, or 1,000 meters over 1 kilometer. So now, for example, if I asked you, if I traveled 325.6 kilometers, how many meters did I go? Okay, so let's take a look. So if you're to start this problem and you were just given maybe something like this, you would obviously want to go find the appropriate equality. It's sort of a roadmap to get you from the unit that you're starting with to the unit you want. Now, this may take one step to do it. It may take a couple of steps to do it. It may take 3 steps to do it. Probably shouldn't take 20 steps, but it's, somewhere between 1 to 3 steps, you can do it. And you may be able to do some conversions in different pathways depending on sort of what conversion factors that you use. So once you have your equality, you really do want to kind of write your two conversion factors. And now you want to just set it up so we have our units in the right place, and we can just use our opposite approach here to cancel. So if we start with the 325.6 kilometers, once again, although it is not written as a fraction, it is up on top. So if it helps you can put the little 1 underneath it. You don't have to. But since the kilometers are on top, that's really important to understand that I need to choose the conversion factor where kilometers is on the bottom, opposite. So here it would actually be this conversion factor that we need to use. So we're going to go with 1,000 meters is a kilometer. Once again, here we're going to multiply what is on top. We're going to divide, if we had a real number on the bottom besides 1, we'll divide by what's on the bottom here. And when we do that, the kilometers, which is on top, will divide out the kilometers, which is on the bottom. They basically will equal 1. And that will leave us the only unit that we see, which is meters, which is up on top. And we will end up with 325,600, I think, meters there. First off, any questions on the setup, the calculation? Again, what I did here is 325.6 times 1,000. And again, you don't really need to divide it by 1, but if it makes you feel better, you can. You'll end up with the same answer. Now that we did the calculation, we could clearly see what units canceled. We could also clearly see what units did not cancel, right, and are left over. We could think about significant figures. So when I break the place and they send me a bill, should I worry about this one? I should not. This is, again, a metric to metric conversion, which would fall under the exact numbers, so you don't have to worry about it. So here we would then default back to what oftentimes happens, the original number, which has how many significant figures? And my answer should have, does my answer have 4? It does. Again, here's why we don't put a decimal point or anything like that. Otherwise, we would have too many. Yeah. Yeah, so if you started with, say, 125 meters, you want to know how many kilometers, Again, this is why you want to set it up like this, which is known as dimensional analysis. So you could clearly see where the units are, because what a lot of people will do when they do problems like this or conversions is, frankly, they don't really know where the units are. And especially if you have maybe a couple units together in a number, it's possible you could have something like miles per hour, right? Miles an hour together in the same sort of number. People get very confused as to, should I divide? Should I multiply? And people oftentimes will end up multiplying when they should be dividing, and dividing when they should be multiplying, and really putting the numbers in the wrong spot. So like you just asked there, if we had 125 meters and we want to know kilometers, now when we go to set up our dimensional analysis, once again, I clearly see meters are up on top, and I want to get rid of meters in this case. So now I actually do need to use this conversion that has the meters on the bottom. And here we would have 1,000 meters is 1 kilometer. In this case, the meters would cancel, and we are left with kilometers. So I know this is good because the only unit that's standing up on top is kilometers, right? Which is what we are looking to get for our answer. And if you have one sort of unit that you want for your answer, so you just want to convert it to like 1 unit at the end, that unit should always end up on top by itself. If you have 2 units, like say you wanted like kilometers per second, the kilometers should end up on top and the seconds should end up on the bottom. And by setting your units and your calculation up like this, you could clearly visually see where everybody is. And you know, hey, am I doing it correctly or not? So now when we do the math here, it's the same math in a sense, because we are going to multiply what's on top and we're going to divide by what's on the bottom. Now in this case, we actually do need to divide that bottom number, right? So in this case, we would take 125. Again, if you want to multiply by 1, you can, but you will get the same 125. And we want to make sure that we hit equals. By the way, when we do these type of calculations, if you have multiple numbers up on top, you could do as many multiplications as you want, but make sure you hit that equal sign at the end. And now we want to divide by the bottom number, which is 1,000. And we end up with 0.125 units are kilometers in this case. Still the same idea. That is still an exact number. This number now has only 3 significant figures, which my answer does as well, right? So that's all good. So it's really important to kind of set these things up this way so that you can see the units cancel. So like I said before, if you had something, say like, let's say we had, let's say we were driving a nice respectable 55 miles per hour, right? So we're driving 55 miles per hour. You know, maybe we're having a nice little drive, you know, it's all right. All right, we're doing 155 miles per hour. No, I'm just kidding. All right. I was on the, no, I won't tell this story. Never mind. All right, so we want to know maybe, hey, we were inspired by Europe. So maybe we want to know what that would be in, say, kilometers per second, right? By the way, you look at your speedometer, right? You got miles per hour in the top, right? Where we look at, and underneath it, it is kilometers, right, per hour, because Europe does kilometers. And so we have that. So in this particular case, right, we need, actually, you know, let's do feet per second. We'll do feet per second. Why not? We'll do that one. A little less conversion since we're getting to the end here. So let's say we want to know, if we're driving 55 miles per hour, you know, how many feet per second are we actually moving? So we need to think about a couple of things to get us there. We need to think about equalities that will get us there, right? And then we can think about the conversion factor. There's really 2 conversions that we need to do. There is, put that up a little bit. All right, we'll do feet per second. Maybe. Okay. So we need one conversion, or maybe a couple conversions, that will take us from miles to feet, right? And one conversion that will directly do that, since we're getting close to the end here. There are 5,280 feet, I get it there, is 1 mile. So that one conversion here will actually take us directly from miles to feet, right? Now, we also need to convert some time, right? We got to go hours to seconds, and there's a couple different ways you could do that. But we do know that 1 hour, right, is 60 minutes, right? And we do know that 1 minute, 60 seconds. I got that. I was thinking about it myself. So in this case, we actually got a few different sort of conversions we need to do. So we want to think about our conversion factors. So for the first one there, we could have 5,280 feet over 1 mile as a conversion factor. Our 1 mile is 5,200. I don't want to write that number today. 80 feet. We also could have 1 hour over 60 minutes. Or we could have a conversion factor that is 60 minutes over 1 hour. We also could have 1 minute is 60 seconds, or 60 seconds is 1 minute. So in this case, we have 6 different conversion factors that we could kind of really pull from those 3 different equalities. And as I mentioned earlier, every equality you can write 2 conversion factors to do so. So the reason we want to set things up like dimensional analysis is if I take my 55.0 miles per hour, right? And by the way, when something is something per something, that's a fraction of 2 units. They're together. Usually the number goes with the first unit and it's 1 of the second unit on the bottom, right? So when I go to do this, we basically just want to kind of do each conversion and take care of it. I'm going to start with miles. I'm not going to worry about the hours. I just want to get miles to feet. And when I'm done, I need feet to end up where? Up on top, which means I need to get rid of miles, right? So I'm going to choose the conversion factor where miles are opposite, which would be this conversion factor, right? And if I do that, that's 5,280 feet is 1 mile. If I stop the calculation right at this point, the units that I have left are what? Feet on top, right? Hours on the bottom. So by doing that one conversion, I am done with the top part of it, right? Now I need to take care of the bottom part. And I know it's the bottom part because I wrote it correctly. I'm not wondering, is the hours up on top or is the hours on the bottom? I can clearly see where the hours are, which means if I want to get rid of hours, hours need to end up where? Hours need to end up in the opposite location. So since hours are on the bottom, they need to end up on top, which means I need to grab this conversion factor, right? And that would give me 1 hour over 60 minutes. Hours on top, hours on the bottom will cancel. What are the units I'm in right at this moment? Feet per minute, right? Which is really close to what I want. I need to get to seconds. I need to get rid of the minutes. I could clearly still see the minutes are on which part, of top or bottom? Bottom, which means to get rid of it, I need to put minutes on top. That means we'll grab this side all the way through there, apparently. So we'll go with this one. We will do 60 seconds on the bottom, 1 minute up on top. Minutes will cancel. The units I'm in right now are feet per second, which is what I'm looking for, right? So now I'm going to do the math to make sure I don't screw it up. We're going to multiply everything across the top. We're going to come back and divide by what's on the bottom all the way across. This is how you should punch it in. You should take 55. You should times it by 5,280. And basically the rest are ones. That's everything on top. Hit equals. I'm now going to divide by what's on the bottom. The only real number is the 2 60s. I'm going to divide by 60, the first one, and hit equals. I'm then going to divide by the second 60 and hit equals. If you would like the right answer, do it that way. Yes, do it individually. You will end up with on your calculator 80.6666667 units are feet per second. Significant figure wise. Am I worried about this one? That is an exact number. This is a exact number. This is a exact number, which means my answer should have 3 significant figures. Yeah. which means I should have something like 80.7 feet per second as my answer. Yes. This will hopefully prevent you from multiplying when you should be dividing when you should be multiplying. We will do more examples next time. Sounds like fun.